Yeah, welcome everybody. Have a great afternoon. Yeah, my talk is about evolving laser system solutions for quantum computing. And I'm leading the product management team for quantum technologies in Toptica. Maybe just for those who maybe have not heard about Toptica yet, so a few key figures. So our technology is focused on various different laser systems. So this includes diode laser systems. We are offering ultra-fast picosecond, femtosecond fiber lasers. We are offering optical frequency combs. Our offering includes fiber lasers and amplifiers. We have products on terahertz generation. And then also we are offering high power laser diodes, so we are at a component level. By the way, also isolators. Some key figures, so company is 560 people strong. Revenue is in the order of almost 130 million. And we are around since almost 26 years now. We have a global presence with the headquarters here in Munich. And then we have different Toptica daughter companies distributed in US, Japan, China, and France. And we have other daughter companies focused on different products, like here the component business, and here this is more our astronomy branch, focusing on astronomy solutions. Now, when talking about the markets, so we have three market segments that we address. So the first one is in biophotonics and microscopy with multiple applications. I won't go into those now. Another market that we are addressing is measurement and processing. So this is about semicon inspections, for instance, holography, lithography, material processing and monitoring. So yeah, all around measurement and processing. And the last one, and this is the one that is of interest here today, this is about quantum technologies and spectroscopy. And yeah, one of the prominent applications that we see there is quantum computing. And this is what we are going to talk more about. What are we offering and what are we looking for also from the community. I mean, I'm very sure you're familiar with the different qubit systems that are around for quantum computing. So this can be superconducting systems, this can be color centers in solids, as we discussed, this can be photonic devices, it can be ion trap systems or neutral atom systems. And the focus of this talk will be on the ion trap and neutral atom systems, mainly because, and we will see this because of the many lasers that are needed there, and also the special requirements that are needed there to the lasers. Now, let's talk a bit in more detail about the requirements for such ion and neutral atom-based qubit systems. On the left-hand side, you see here some exemplary qubit systems. So this can be ion-based systems like terbium plus, calcium plus, strontium plus, barium plus, and again, this is exemplary. There's also neutral atom-based systems, either based on strontium, can be rubidium, strontium, Rydberg, rubidium Rydberg, or can be ytterbium labs. So there's all types of different qubit systems. I don't want to go into the level schemes, but if you look into them in more, if you looked into them in more detail, you would see, yeah, there's many different laser transitions, also with very different requirements to those lasers in terms of power level, but also in terms of frequency stability and with respect to line width. And looking at those parameters, so first of all, looking at the wavelengths that need to be covered. There's many different wavelengths that are needed, ranging from the UV all the way up into the mid-infrared. Looking at the power levels, what we see as requirements ranging from a few milliwatt or even in the milliwatt range up to many or at least a few watt. Frequency stability, again, depending on the transition that is addressed, it ranges in the range from hertz to megahertz. Line width requirements similar. For some of the lasers, especially for the gate lasers, so the qubit gate lasers, phase noise has to be very low. And another requirement that we often see from customers, especially if customers want to move more to commercial applications, is convenient control. But even in a university environment, this is key, because systems are getting quite complex, so you want to have a convenient control of the systems. So that's for the requirement side. Now let's look on what Toptica is offering. So first of all, we address this need for many different wavelengths and are therefore flexible whenever there's changing requirements or new requirements on the transitions. So even for a given system, these can change. So because customers, they tend to change then the gate laser, for instance, from different gate laser configurations. So all wavelengths is key, and we are addressing that with our highly coherent tunable diode laser systems. So those can be non-amplified systems, it can be our amplified systems, it can be the combination of amplified and frequency doubled, or even quadrupled. And so that gives us then the wavelengths in the blue at high power, or even in the UV, depending on the exact requirements. Another offering, and that's rather new, probably you have heard about our acquisition of formerly Azurelight systems. So with them, we got into our portfolio high power amplifiers and fiber lasers. So that's great. It just boosts the power that we can get out of our lasers. And another portion of the portfolio is, and that is needed for ion or neutral atom-based quantum computing systems, you need stable frequency reference systems. So this can be either a wavelength meter, it can be a spectroscopy cell, it can be a frequency comp, or it can be an ultra-stable laser, or some cavity solution that stabilizes the lasers. Now, what do we see as a trend? We see a trend towards complete laser system solutions. So customers, they don't want to bother really in integrating individual lasers, but they want to have a complete laser system solution. So typically, these should be 19-inch rack mounted and fiber coupled. And fiber coupling then ranges again from the UV wavelengths all the way up to, at least to 1770 nanometer, can be even higher in some of the cases. The system should be rather modular, so that you can mix and match different types of laser solutions. It is supposed to be fully integrated, and that's what I actually mean by complete. So it should be integrated and frequency stabilized in the end, so that customers don't have to bother with the frequency stability any longer. And then we talked about convenience before. This is enabled via full remote control and user-friendly interfaces. So that, in a nutshell, is what we are offering in terms of complete laser system solution. And another trend that we see is customers are looking for miniaturization, and we have done here a nice development in our Eagle Yard branch, focusing on mini ECLs. Yeah, so that's in a nutshell what we are offering as Toptica as a product. Now, where can the ecosystem help us? So one topic is actually mentioned already here, and that's the fiber coupling. So fiber coupling is a key topic for us, essentially because we need to deliver the light to the customer's experiment, and the most convenient here is fiber coupling. But especially further down in the blue or even in the UV, there's not really good and high power tolerant fiber coupled solutions. So anything in that direction would be of great help for us. Now, I want to give you an example of such a complete system solution that we have been shipping and that is operating today at the customer's premises. So this is a strontium Rydberg laser system solution for a quantum computer built up at the University of Stuttgart in the framework of QRIT Demos, which is a German government-funded project. And you see, the system comes with many different lasers. So it's a total of 16 different laser systems. Actually, some of the lasers are double, so it's even more than the 16, but it's 16 different laser systems, quite complex system. And you see here the complete laser system nature. So lasers, depending on the exact requirement to that specific transition, they are locked to a wavelength meter. Some of the other lasers are locked to our frequency comb. And in turn, for long-term stability, the optical difference frequency comb is locked to an ECDL, or actually for line-width narrowing, it's locked to an ECDL, which is again locked to an ultra-stable high-finesse cavity. And that gives like comb teeth for the complete spectrum in the range of 1 to 10 hertz line width, so super narrow line width. And yeah, so this is just an example from last year, so in which Tilman Pfau and his team, they trapped atoms by using optical tweezers. And that already completes my talk. Thanks for listening, and I'm looking forward to the discussion.